Okay, in this presentation we are going to look at a worked example concerning the difference in proportions. Okay, now what we're going to look at in this particular example is the effect of sample size that it has on the outcome, or if it has an outcome, or if it has a difference on the outcome. But anyway, so we have a market research survey. A market research company is carrying out a survey of adults in two large towns either side of an international border in order to judge attitudes towards a controversial internationally broadcast celebrity television program. Take your pick, basically. This is an old question when these were new. Anyway, the following table shows some of the information obtained by the survey. So we have the sample size in both cases, town A and town Z. It's 50 and 50. But the number approving is slightly different on both sides of the border. So in town A it is 26 and in town Z it is 22. Conduct a formal hypothesis test at a 5% significance level of the claim that the population proportion of approving of the program in the two towns are equal. Would your conclusion be the same if in both towns the sample size had been 100 with the same sample proportions of approvals, i.e. 52 and 44 approvals out of 100? Okay. So what we're going to do here is conduct a formal hypothesis test, and we want to test the claim that the population proportions approving the program in the two towns are equal. So this is a two proportion Z test. Essentially what we're looking at here is there a difference in the proportions. Okay. So the null hypothesis is PA equals PZ. Okay. That is PA and PZ are the proportions of approvals in town A and in town Z. Okay. The alternative hypothesis, HA, is that they are not equal. Okay, so essentially what you're looking for is usually what is sort of suggested by the data is usually expressed using the alternative hypothesis, with the null hypothesis being the expression of the exact opposite of the alternative hypothesis. Okay, so we're interested in really is there a difference. So we sort of express that using the alternative hypothesis. We look and see if there's a difference, and when we are writing our null hypothesis, we express the exact opposite of the alternative hypothesis. So if the alternative hypothesis is that there is a difference, that they're not equal, the null hypothesis will say they are equal. Okay, just a quick recap on that. But anyway, when you're conducting a hypothesis test, it's always important to write this out and just explain what the terms are to a reasonable extent. Now, town A, NA equals 50, and XA, the number of successes, in this case the number of approvals, is 26. Town Z, NZ is 50, same sample size, NZ is 22. Okay, so the sample proportions P hat A and P hat Z are 26 divided by 50, 0.52, and 22 divided by 50, 0.44. Also in this case, because we are carrying out a hypothesis test for the difference in proportions, we will need a very specific value for the pooled proportion. Okay, always pay attention to the required standard error calculation that you will need in various different inference procedures such as confidence intervals and hypothesis tests. In this case, you will need the pooled proportion, okay? And so in that case, what we are going to do is the pooled proportion is essentially the number of approvals out of the total number of people surveyed, disregarding which group they're in, okay? So it's XA plus XZ divided by NA plus NZ. Okay, so it's basically, we asked 100 people, 48 said that they liked the program. So we have 48 out of 100. Basically, it's just the overall sample size disregarding which town they are in. Okay. Now, the standard error. So this is the standard error formula. Okay, and we're going to use the pooled proportion in this calculation. This first element of this formula should be given to you in an exam paper somewhere. Okay, it's rare that you have to memorize these. It's the P hat, which is the pool proportion, times 1 minus P hat, the complement of the pool proportion, times 1 over NA plus 1 over NZ. Those are the inverses of the sample sizes from both groups. So P hat is 0.48. 1 minus P hat is 0.52. In both cases, we have 1 over 50. 1 over 50 plus 1 over 50 is essentially 0.04. So what we have to do is calculate the square root of 0.48 times 0.52 times 0.04. A little bit of calculator work. We get the square root of 0.009984, which is approximately 0.0999. And just as a quick remark, it's often the case that there's a lot of digits here. There's a lot of decimal places that you have to go to. Probably 6 decimal places or 7 decimal places is usual in the penultimate part of these calculations. When you're about to calculate the square root, just don't avoid it. Just go to the 6 or 7 decimal places. Okay, so it's just short of 0.1 there. Anyway, so our test statistic is calculated as the point estimate, which is the observed difference between proportions, divided by the standard error. Okay, that's just a general sort of structure for a test statistic. I'm not going to get into it here so much, but just to remark upon that. So our test statistic is the point estimate is the difference in proportions, P hat A minus P hat Z, which is 0.52 minus 0.44, divided by the standard error. Well, the difference in proportions is 0.08, and our standard error is 0.0999. So our test statistic is approximately 0.80. Okay. So at a 5% significance level for a two-tailed test, recalling that this is a two-tailed test, the critical Z value is approximately going to be plus or minus 1.96. Okay. So since the calculated Z score 0.80 is within that range, it's less than or it's between 1.96 minus 1.96 or to 1.96. We fail to reject the null hypothesis. Just as a quick remark there, a different approach that some people take is they compare the absolute value of the test statistic just to 1.96, just to the upper bound. Okay, and just as a remark, that's some approach that some people take. I think it's quite good actually, but it's not really important here. So at a 5% significance level, there's not enough evidence to reject the claim that the population proportions approving the program in the two towns are equal. Okay, so essentially we fail to reject the null hypothesis. There's not enough evidence. There's not enough evidence here in this data. Now this is sort of the point of this question, actually looking at the effective sample size. Okay, so what we're going to do is go back out and do the survey again, and it just so happens we get the exact same proportions. Okay, P hat 1 is, or P hat A is 0.52 and P hat Z is 0.44. Okay, so we just happen to get another 26 people in town A that like the program, and we just happen to get another 22 people in town Z that like the program. Okay, so really everything's here the same as before, but really just the sample sizes are 100 as opposed to 50 in both towns. And we're going to sort of see what effect this has on our calculations. So the pooled proportion again is still 0.48. That doesn't change. Okay, but essentially what is going to change now is the standard error calculation. So we have the square root of 0.48 times 0.52, which is the pool proportion times the complement of the pool proportion. But the bit here that is different now is the square root, 1 over 100 plus 1 over 100. That is 1 over NA plus 1 over NZ. 1 over 100 plus 1 over 100, that is 0.02. So we're looking for the square root of 0.48 times 0.52 times 0.02, the square root of 0.004992, which is approximately 0.0707. Okay. So we get a Z score of 0.52 minus 0.44 divided by 0.0707. Okay, you might notice that number is actually smaller than the previous example, even though we're dealing with bigger numbers. That's the point. Yes, it is. So it should be smaller if there are larger sample sizes. Okay, so previously it was 0.999. Anyway, it's good that it's smaller because it makes the test statistic larger, basically. So a little bit more effort going in here. So anyway, 0.08 divided by 0.0707, we end up with a test statistic of 1.13. So again, this is it within the range of plus or minus 1.96. So at a 5% significance level for a two-tailed test, the critical critical Z value is still plus or minus 1.96. So we're still within that range, so we still fail to reject the null hypothesis, okay? But the numbers have changed around now. So it's essentially the effect on the standard error, the test statistic, and the standard error is what we're observing there, okay? Conclusion, even with the larger sample size at a 5% significance level, there would still not be enough evidence to reject the claim that the population proportion improving the program in the two towns are equal, okay? What may happen if you doubled it again, that may happen. And you can give that a go if you want. Okay. We'll leave it there.